Good afternoon, everyone, and welcome to our session on a guide to advanced simulation for SOLIDWORKS Premium and simulation users. So before I get started, I have two announcements. We have printed the agenda of the session for those who want to follow along. So I think Mark can give them along. And the second is, it's the last session of the day for most of you, if not all of you. So we have brought candies to help you stay awake. But if you fall asleep, I'll take your candies away. And the tip is, eat your candies to stay awake. So my name is Maidwan. I'm an industry consultant at Dassault Systèmes. Oh, am I too loud?
No, you're fine.
Oh.
I'm just not doing my job.
Okay. So prior to this role, I was the product manager for SOLIDWORKS Simulation for 4 years. And before that, I was an application engineer at ANSYS. And today, I have with me Mark Pickering.
Welcome, everybody. I've been doing finite element analysis for about 30 years. I'm part of the Simulia group, and I've been with them for the last 15 years, 14, 15 years. And the main thing that I do is I am talking to your resellers about our software and what it does so that then they can talk to you.
Okay, so by show of hands, how many of you are using SOLIDWORKS Simulation or simulation in SOLIDWORKS Premium? Yes, so this session is for you. So welcome again. And the goal of this presentation is to guide you through the transition from SOLIDWORKS Simulation, or the simulation, in SOLIDWORKS Premium to the 3D experience simulation or the platform sim. So first of all, what is 3D experience? It is a unified platform that integrates all of the best and most advanced technology from Dassault Systèmes. So you are familiar with SOLIDWORKS, but you should know that Dassault Systèmes owns other leading brands such as CATIA, Simulia, Enovia, among others. And when you work on the platform, you have access to all these different disciplines. So design engineering, simulation, manufacturing, governance, which is data management, also marketing and sales. So why simulation on 3D experience? The simulation on the platform is powered by Simulia, a leader in the simulation market. And customers choose 3D experience simulation for the Abacus solver, implicit and explicit, general contact, its advanced and extreme nonlinearities, and cloud computing. And we're going to cover all of this today. And I think Mark has a bonus point for you, which is fatigue and Wellman fatigue. But you have to wait for him to tell you all about that. So, for the agenda, we're going to look at the simulation, the feature tree in SOLIDWORKS Simulation, and explain how each of these items is performed on 3D experience simulation. So we're going to start with the connector from SOLIDWORKS Simulation. Then we'll talk about geometry, then the assistant, then model scenario results, or the MSR model, then materials, interactions, mesh, solving, which is cloud computing, and then advanced and extreme nonlinearities. So first, let's get started with the connector from SOLIDWORKS Simulation. You can use this connector from SOLIDWORKS Simulation to transfer SOLIDWORKS Simulation studies and features to the platform simulation. So by using this connector, you will save time because you can reuse some of the features that you already defined in SOLIDWORKS Simulation. So you don't have to redefine them again. So let's see how it works. To use this connector, so when you are connected to the 3D experience, to the platform, you'll have this blue side panel that allows you to save your data to the platform. And to use this connector, you'll go to the lower lower right of the screen and use this tab, Simulation, and select Create a Structural Simulation. And when we select that, the software says that the simulation has been created and is ready to use in 3D experience. So let's open it. And here you can see that both simulation studies, the nonlinear and static, have been transferred to the platform. And in the simulation status, you can see what has been transferred. So we have two columns. On the left-hand side, the simulation features from SOLIDWORKS Simulation, and the right-hand side, the features that have been transferred in 3D experience simulation. So what has been successfully transferred? Materials. So in this case, I have assigned material from the 3D experience library, so they have been transferred. I don't have to reassign material when I go to the platform. Connections. The component interaction have been overwritten by general contact, whereas the individual connections have not been transferred. Boundary conditions, the fixtures. So the fixed boundary condition and the symmetry boundary conditions have been successfully transferred. And then meshing, the default mesh specification in 3D experience simulation have been transferred. So some of them are successfully transferred, not the others would be overwritten by the default on the platform. While this connector is functional, most users prefer to transfer SOLIDWORKS CAD directly to the platform and set up their simulation from scratch. And that's also what we recommend, because the associativity is not going to be kept, just like the connector that we're going to talk about today. So that's the next topic, which is geometry, and which is the transfer of SOLIDWORKS geometry, so SOLIDWORKS CAD, directly to the 3D experience. And this is the method that we recommend. To use this connector between SOLIDWORKS and 3D experience, because this connector will maintain the associativity between SOLIDWORKS CAD and the platform. So what it means is that if you modify your geometry in SOLIDWORKS, you don't have to do the setup again. All the changes will update, and you don't need to redefine the setup, which can be time-consuming. So to use this connector, you use the side panel. When you connect it, you select the geometry that you want to save, right mouse button, and say Save. Then go to the compass and select the app that you want to use. In this case, I'm choosing the scenario app. And here, I can give a title to this simulation. And here it is. The geometry has been imported to 3D experience simulation, ready for me to set it up from scratch. So the next topic is the assistant. For those who are, actually, I forgot to ask, how many of you have used 3D experience simulation? Not a lot. So I hope that after this session, you'll be pumped up and ready to go and to get started. Okay, so for those who are new, who are just getting started, we recommend that you use the assistant. It's a great tool that will help you go through the setup and go through all the steps that are required to successfully set up your simulation on the 3D experience. And actually, I am going to show you the assistant. So here, I have a gear shifter, and I promise fun models, but we can imagine it. So let's think about this gear shifter of a fancy sports car. I don't know, Ferrari or Lamborghini or Bugatti, I don't know, just imagine, right? That could be fun. So let's set it up using the assistant. And for boundary conditions, I am going to fix this face here, then apply a symmetry boundary condition to these two faces here. Then I would apply a displacement to push down this cylinder. So actually, this motor has two components. One is a metal cylinder, and the other one, a rubber piece part for this gear shifter. So I'm going to push this metal piece down by 40 millimeter to push down this gear shifter. And for interaction or for connections, I'm going to use a bonded contact to weld this face of the cylinder and this area of the rubber piece. And use general contact with friction everywhere else. And so that's my boundary conditions and interaction. So the assistant is gonna guide me through all the steps that I need to complete in order to set up this simulation. So let's get started. I'm going to, so the goal here is to turn this red circle that you see here into green check mark. So we also go from top to bottom. So let's get started with the setup. So I'm going to select a finite element model. I'm going to create a brand new one, and I can call this a FEM2. And because this geometry can be swept mesh, meaning I can create a mesh and just sweep it around, I'm going to select Sweep 3D Mesh. And in this case, I'm going to use 36 layers to sweep this face all the way to the other face. And that is the setup. Now, what type of simulation study do I want to choose? Here, I'm going to choose a static step, which is a nonlinear static in SOLIDWORKS simulation, and give a 0.1 second. Now, in the connection, I could use tools like virtual balls or springs or virtual pins, but in this case, I don't have any. So I'm going to go to the next one and define interactions. Here, I'm going to choose to define two contact properties. One for the bonded contact in this area, and one which is frictional everywhere else for this general contact. So let's define the bonded one. For the bonded, I'm going to use a rough friction and not allow any separation. And the other contact property, which would be the friction one, let me give a friction coefficient of 0.1. And now here, I'm going to specify this general contact, saying I'm going to use general contact with friction everywhere else in this model here. So even if there's a self-contact, it will use this frictional contact, except for these two faces. So let's go and select them. And use bonded. Let me unhide this face here. And that is how I set up my contact, my interactions. Actually, I have an issue with my contact here. This one is friction. Let me go and select this one here. It's bondage. Is it the assignment that? Oh, I think.
Cancel it.
I have to set that.
Which one was the one you've just created?
Fem 1. Okay, I did run a previous model before, so a little trouble here. Okay, so that is for the contact. The next step is the boundary conditions. So I am going to use clamp, which is basically fix this face contact. And then for symmetries, use this, these two faces for the planar contact, the planar symmetry. And the last boundary condition is to apply this translation. So using a minus 40 millimeter and fix the orthogonal translation, which is fix the translation in the X and the Y. And that's how I set this up. Now I can go and verify my mesh. It is looking good. And here in Simulate, I can go and check that all the setup are properly done, or I can go directly and solve it. In this case, I'm just going to use the local. I will talk about cloud computing later. So let's just get this started. And while it's running, it should just only take a minute or two. Let me see if there's any questions so far about the material that I just covered. Or if for those who haven't got their agenda, we have some here. And we are at number 3, which is assistant.
Hi.
Oh. And we have candies left for those who are feeling a little snoozy, even though we're trying our best to... I'm sorry?
Simulation.
Uh-huh.
No. There was a material already applied from SolidWorks that was compatible with 3D Experience.
Product.
So I just passed straight through.
So you have solid simulation, is that right? Yes, no, this, oh, yes, go ahead.
Yes. Yeah, so that's a little bit tricky in this particular
roles.
situation.
I can give you my business card and we can talk about that after the session. Is that? Okay, so it has solved and we can close the statues or you can go and get all kind of information. You know, not gonna go through that today, but we can look at the results, the von Mises stresses or the displacement, and you can see that the assistant also guide me through all the post-processing quantities that I might be interested in. So that is how you use the assistant. So for this simulation study, which is fairly simple, you can set up everything with the assistant. But, so going from SOLIDWORKS simulation to platform sim, we highly recommend you use the assistant. But for simulation studies that are more advanced, more complex, the assistant might not be sufficient. And that's what we're going to talk about next, which is the model scenario results, or MSR for short. And this, I would say, has been the most important concept that helped me when I transitioned from SOLIDWORKS simulation to 3D experience. So I would say the meat of the presentation is really to understand this, even though you can use the assistant for most of your applications. Okay, so in SOLIDWORKS simulation, all the setup is being performed in one window or one app. On the platform, the setup is modular. So that gives you more choice, more control, more flexibility, and we'll talk about the benefits later in a little bit. And so the setup is modular and it's organized in 3 apps. Model, scenario, results. So 3 apps. Model defines the object that you want to simulate. So that would be the geometry, material, and the mesh. Scenario defines the conditions, the boundary conditions that you want to apply to the object that you want to simulate. So that would be boundary conditions, or in here, fixtures and external loads. And results, same as in SOLIDWORKS Simulation, it would be results, but it will be in a different app. And so you go from 1 app to 3 apps on the platform. And these 3 apps correspond to 1 assistant. Now, I love the assistant so much when I first started that I'm still using it today. And when I need more, then I go and, because I understand the MSR, and I get access to MSR. But somebody like Mark, I don't think he used the assistant. I mean, no, he doesn't. So, but you know, for most of you, use the assistant to get started. But we're gonna explain to you more in detail. So let's do the mapping of the SOLIDWORKS simulation features to this model scenario results. So parts, geometry, and mesh map into model. So again, model defines the object that you want to simulate. So the definition of the model. Next, the connection map to model and scenario. And that's why we brought Mark in, who explained to us in detail how that works. And then scenario, fixture and external loads will map into scenario, because scenario is where you define the boundary conditions that you want to apply to the object that you want to simulate. And then last, easy to memorize, results map into results. So how does that work in the interface? First of all, you want to pay attention to the upper left corner of your screen, because it has the name of the app. And in this case, it is model. So I would ignore maybe all the other words, but just remember that it's model scenario result, MSR. You know, you can ignore some of the longer names. And the feature tree in 3D experience simulation is also organized in model scenario results. Now, the action bar is also organized in model scenario results. And this is where you go to switch from one app to another. So let me show that to you in the interface. So let me close that system. We don't need that. And so here, I am, in which app I am here? Yes, thank you. There's more candies for those who participate. So if I want to go to, for example, model or scenario, I would go here in the action bar, and let's just select model. And here, you can see in the upper left, that's the name I am in the model app. And you can see the functionalities associated to this model, which is that I have the mesh, I have the materials, and I have functionalities that define the object, which are abstractions, properties. So if I want to switch to the scenario app, I can go here, click on scenario, and now you can see very different functionalities, so scenario is where you define the boundary conditions or the condition that you want to apply to the model, right? So it would be initial conditions, boundary conditions, predefined fields. So very different from what I have in model, right? And for example, if I want to go and launch the model, I can't do that in model. I have to be in scenario. So you see, I can go to simulate here and launch it. But if I go back to model, so here I can go and double click on in the feature tree, and I'm back to the model app. And here I don't have a way to simulate it. So understanding this concept of model scenario results is really helpful in understanding how the setup is being performed, and also understanding how data is being organized in 3D experience simulation. Okay, so that was the important part of really, understanding that to understand where you are in the app, right? In the interface. The next topic is materials. And I touched upon this a little bit earlier. If in SOLIDWORKS you apply materials that are from the 3D Experience material library, so shown here, then that material would transfer to the 3D Experience simulation. And you don't have to redefine the material again. But if you apply a material from a different library, such as the standard SOLIDWORKS library or the SOLIDWORKS DIN material library, so from a different material library, then that material will not be transferred. And you would have to define the material again on the platform. So the material on here is called also the master material. And here you can see the extensive library of material models in 3D Experience. And you can see that there are a lot of material models that are not available in SOLIDWORKS simulation, such as rock and soil, concrete, crushable foam, vinilo. I mean, like there's a bunch of them. And if you want to use these material models in your simulation, you would want to go to the platform to do that. Because we all know that without the proper material model, your simulation will not accurately capture the real world scenario. And for this particular gear shifter of our fancy sports car, right, we need a rubber material, and we have in SOLIDWORKS simulation 3 hyperelastic material models, and on 3D Experience simulation we have 10 hyperelastic material models plus the user-defined one. And for those who have material data from some test lab, you can use the material calibration, which is powerful and widely used by a lot of users. And with that, I'm going to hand it back to...
Thank you, Meg. Okay. So in this next section, we're going to be talking about interactions. And in SOLIDWORKS, this is going to be under the connections branch, as I'm sure you're all fairly familiar with. Before I get into the 3D experience side, though, I do want to just recap a little bit in SOLIDWORKS. So in SOLIDWORKS, we're defining essentially pairwise contact. We've got set 1, set 2. Set 1 can be surfaces, edges, vertices, and set 2 will be a surface. And this works great for things like the tutorial model of this little clip, because we've just got a single surface in set 1, single surface in set 2. For more complicated models, there is also the automatic detection. So we can put in a tolerance and then find all of the contact pairs that are within that tolerance. So all of the individual contact pairs between the gasket, the pipe, the bolt, the nut, etc., will all be detected, and we could obviously have multiple of these pipe connections in a full assembly. Pairwise contact is also available in 3D Experience. It's been a standard approach for a long time now. But one of the things where typically it becomes trickier to start defining is when we consider large relative motions as part of our analysis. So if I'm going to go back here now to this clip, and we're going to take that red part, and if it's only moving a little bit, we just need that surface. But if I keep on pushing that red part inside the clip, then we're going to need to develop contact on the fillet surface and maybe even on the flat surface as well. And typically this sort of thing will be something that you need to define manually because you can't choose an appropriate tolerance that is going to grab a sufficient region to grab these surfaces without grabbing things that you don't want to get. Again, for this clip, fairly straightforward. There's only 3 surfaces in one of the sets. But what about a model like this? Here I've got a ball that I am projecting inside this field of strands. It might be hard to see that, but there is 180 strands in this particular section. No particular reason, I just happened to choose that sort of size. It could be any number of strands. Defining 180 contact pairs themselves would be fairly problematic manually. But if we look at what actually happens in the analysis, these strands are very flexible. So when that ball impacts them, any one strand could hit any other strand or fold on itself or hit multiple strands at the same time. So it is very important to capture all of the contacts that can occur. Now, full disclosure, I did not use contact pairs for this. Maya's already mentioned a couple of times this concept of general contact. Are you familiar with general contact? Is that something you've heard of before, or this is a brand new term to you? Brand new? That's fair. So this is something that we've had with Abacus for a while now. And in general contact, as we can see here, it's one single feature on the feature tree. And here we've got defining the general contact in the interactions tab on the bottom. Yep. And if I go into that if I go into that dialog, we can see that basically, by default, it will include all pairs, all surfaces. That includes self-contact. So you don't need to set that up separately. All surfaces to all other surfaces, including themselves, is the default for general contact. And then I just pressed OK. Now, you will maybe notice, I mentioned about the model scenario results, and this typically general contact is defined in the scenario. With FD01 that was released, I think, 8 days ago, there was a new option set up which is in the model. So now you can define contact in the model. We have previously mentioned here that in general, if you're just trying to think about going into 3D experience simulation, the assistant is a good place to be. In the assistant, you can set up general contact. Mai did that in her demo. That would be the bit in scenario that we mentioned. But having contact in the model, we get this dialog. If you're going to build things manually, this would be my recommendation. It's a bit more of a streamlined interface to what you saw when Mai did it. So it's a bit closer as well, I think. It's obviously not the same as the contact interface that you have in SOLIDWORKS Simulation, but it's fairly clean, it's fairly straightforward. You've got your major options, you can choose various bits and pieces. And by default, you'll notice again, this is all and self. This is general contact in the background, so it's still using that same definition. You don't need to go through contact pairs. The default property is frictionless open-close contact. You can create your own property, as Mai did, to put friction in. The other reason I would recommend this for you is there is by default a bonded option here, so you don't need to set that up. Admittedly, it wasn't that many clicks, but anything that helps, helps. Now, if we go back to Mai's example, she was setting up general contact everywhere, and then she was overriding it where the gear shifter and the boot met. And you can do the same thing here using this little icon at the top. And if you do that, it will choose to add a new bonded interaction. And whenever you specify anything explicitly for surfaces, that will override the default general contact. So it's all surfaces general open-close contact, but here, because it was specified, it's bonded contact here. That's exactly the same approach that Mai had in her model as well. So that was kind of the main thing. And I think for contacts, this is where I would sort of recommend you start thinking about 3D experience. If you're ending up with large numbers of parts with large relative motions and it's just getting complicated to define the contact pairs, we can use general contact and we can run through all types of different analysis situations. This clip going into the slot is showing edge-to-face contact and developing through the analysis. The tissue is sort of showing self-contact on the face. Here, this drum rolling, it might not be obvious because it's being shown rendered, but this is beam-to-beam contact as the wire rolls on. I'm not sure, I don't believe SOLIDWORKS Simulation has that capability, but that is here. And then there's obviously beam to solid contact, and the paperclip is actually a beam to a shell contact. Again, they're just shown fully rendered. And we'd still support all of the things in general contact that you're used to through SOLIDWORKS Simulation. So surface to surface, edge to surface, vertex to surface, as well as edge to edge contact. Right.
Thank you, Mark. Okay, I'm back to talk about meshing. So, in order to obtain results, we need a mesh, both in both software, right? In 3D experience simulation, there's a new terminology, which is FEM, or finite element model. And a FEM is slightly different from a standard mesh that we're familiar with because it includes section and connections. And the benefit, the main advantage of a FEM is for the same geometry within the same simulation study, I can have multiple FEMs, meaning I can have multiple mesh refinements within the same geometry and within the same study. So for example, for this car crash, I know it's not a fast, fancy sports car, but I can get a FEM with a coarse mesh for a frequency study, for example. And for the same geometry and simulation study, I can have another FEM with a fine mesh to simulate a front car crash, just like you see here. You don't want to invest fine mesh everywhere in the model, right? You just want to refine it in the front. And I can have another FEM with fine mesh on the side for a sidecar crash. And I can go on and add many, many FEMs. And all of that for the same geometry within the same simulation study. On the platform, we call it physics simulation. But that's really something that is very powerful that we can't do in SOLIDWORKS simulation. How do you do it today, right? In SOLIDWORKS simulation, we'd have to overwrite the existing mesh with a different mesh density in order to get results. Or you have to copy the study and apply a different mesh. And the modular setup that I explained earlier, model, scenario, results, right? Having 3 different apps is what enables us to have multiple FEMs. And so multiple mesh refinement and multiple studies within the same study. So the benefits of having multiple FEMs is that you will save time. There's no need to have multiple studies for different mesh refinements. You can do all of that within one simulation study. You will be able to improve performance by optimizing the mesh refinement. So again, you just want to have a fine mesh in the front, on the side, depending on where the car crash is. And you will be able to enhance accuracy by having the right mesh density. Oh, is there a question? Yes, go ahead. To mesh large assemblies? So, Mark, do you want to take that on?
Yeah, so I assume you mean like go through, run a mesh on many parts inside an assembly. We're not showing it here, but there's a batch meshing routine where you can set up procedures and say, for these types of parts, we want to do this type of mesh. For these types of parts, we want to do this type of mesh. And then you just sequence that all through and it will create a mesh with all of those individually done. No, you could either just do all parts at once. Like if you only want to do like a sweep mesh on every single part, you could just do that all in one. If you want more fidelity, like you want every part that is got a tag of shell to be shell meshed, and every part that's got a tag of hex to be hex meshed, and every part that's got a tag of tet to be tet meshed, you could define those procedures and then just run that through and it would do all of them. So as variable as you need. Mechanical property of the water? It's going to depend how you're defining that as a material. So there'd be various ways of doing it. I think I probably need to talk to you individually about that and how you want to go about doing it.
We can talk a lot about large assemblies, between, if you run into limitation with SOLIDWORKS simulation, the platform has a lot more power just because we put the best technologies, the mesher and whatnot on the platform. So, but we can, let's us go get through the material and then we can have a much longer conversation, yeah? Okay, so the default meshers. If you are not specifying anything on the platform, it will use the tetrahedron mesher for solids and surface triangle mesher for surfaces. And a lot of users prefer hex mesh because of its accuracy, because of its efficiency and stability. And you can do that on the platform by using a sweep 3D mesher. I show that with my gear shifter. Or you can use the surface squat mesher for shells. And in addition, we have the partition mesher. So here in this part, you can see that the yellow part is swept mesh, and the orange part is tet mesh. And so you can have a complex part that can't be all swept, but have a combination of both. And when you use this partition mesher, the software automatically connect the two regions in the background for you. So convenient and time saving. And the next topic is solving and cloud computing. So common needs among our simulation users is to get results fast, very fast. We have no time to waste, right? Well, you can do that with cloud computing and high-performance computing. So instead of running your simulation on local with your local machines, you can get results a lot faster without cloud computing. So there's no need for you to invest in expensive hardware and maintain it and keep it up to date. The cloud computing from Dassault Systèmes does all that for you. Our servers are more powerful, more robust, more up-to-date than most of the local servers. And to see how to use cloud computing, so here I have to go to scenario, right? And in simulate, I have the option of choosing local or cloud. And when I choose cloud, I have many configurations. So depending on the product that you choose, it's 8 cores, but you can go all the way to 192 cores. and this is the memory and 4 nodes. So that's, so the cloud computing is fully embedded with our 3D experience simulation products, and it's really to use. You just choose whether you want to solve locally or on cloud. And so let's look at some cloud computing speed up. So this model is an implicit one with contact. It has 17 million degrees of freedom. This graph is on the x-axis, the number of cores, and the y-axis, the solve time. So here, going from 8 cores locally to 144 cores on cloud, we achieve a time reduction of 95%. So pretty amazing. And we talk about car again, where in the second example is the one of an explicit with general contact. It has 29 million degrees of freedom, and going from 18 cores locally to 144 cores on cloud, we achieve a time reduction of 91%. So just some example to show you the impressive scalability and performance using cloud computing. So you can save a lot of time by going on the cloud. So if you have large assemblies, meshing really large, you can use cloud computing and free up your machines and save a ton of time. And
Okay, so this last section is going to be sort of advanced things and extreme nonlinearities. We've talked about general contact and how we can use that to get easily defining the contact in a large assembly with large relative motion. But defining contact and setting up the model is only one part of the battle. The main problem usually is in solving these complex problems. Now, this might not seem particularly complex. We've just got a rubber shaft with a steel sleeve. We have a sinusoidal-like interface. One thing I do want to point out, though, is we are now looking at a more realistic friction coefficient. And so you probably see a friction coefficient of 0.1 very commonly. The lower the friction coefficient, the better it tends to be for stability of the simulation. But if you look at any friction chart, 0.1 is a pretty slippery surface. So here we've just particularly got 0.4 in this particular model. And what we want to do is we want to rotate that rubber shaft by 1 notch, and then look at what is the moment that we are dealing with in order to progress through that. This is actually set up in SOLIDWORKS Simulation, and it gets through to about 13% of that one rotation, and it took about an hour to do that. Now, is this something that any of you have experienced, that you sometimes have difficulty just getting your analysis to work? You've got the contact set up, all of that is fairly straightforward, but just getting it to solve is troubling. Okay. Now, this is a static analysis, and the messages, I won't go into any great detail on this, but it's basically complaining about singularities and stuff like that. One of the ways to usually get more progress through analysis is to do a dynamic analysis. I think this is actually an animation of the static analysis. But if you do a dynamic analysis, you can deal with instabilities in the stiffness because you've got a real time scale, so you can see things like snap-through buckling and stuff like that. And indeed, in SOLIDWORKS Simulation, we end up getting much further. We've got to 25%. You may also notice the time scale that we're looking at now as well is 16 hours. So we still have not got to the end, and we have spent a lot of time dealing with the numerics in the background and before we failed as well. This would be another reason why you might want to consider looking at 3D experience. So this is the same setup. But you can see that we've got the torque chart here. We've got an animation showing the one section revolution. And there is a little bit, maybe the cheat here. This is run on 8 cores on the cloud. Most of the roles that you're going to be looking at will have 8 cores embedded compute, so that just comes out of the box. But it did take 32 minutes on here. So it is shorter than even the 1 hour. I don't know how many cores were used in SOLIDWORKS Simulation for that 1 hour, but we've got to the whole end in 30 minutes. So that would be my second recommendation, really. If you're having problems defining the contact setup, general contact is a good solution for that. If you're having problems running the setup, then there may well be tools in 3D Experience where you can actually get that converged and get through and get the information that you need. We're sort of running out of time a little bit, so I'll skip over these next bits, but these next ones are basically just examples of types of simulation that do get run. So we are concentrating a little bit on contact here because it is by far the most common nonlinearity that most people are interested in. And we've got all sorts of things going on. Many individual strands in this wire and this wire being twisted. So defining all of those contact pairs again becomes problematic. The door impact, the prosthetic test. We can also deal with things where they collapse in on themselves. I did mention that in general contact, the default is all surfaces, including to themselves. So sort of progressed on, but these inner chambers, if they're a single surface, or these walls might buckle, or as we're seeing here in this column, this one flat side is now rippling on top of itself. And then we're getting more and more deformation. That's basically what we're sort of showing here. Stamping and the permanent deformation that's coming on. A rivet going through, the rivet deforming and permanently setting, as well as the plate that it's in. And then on the right for you, blow molding, where the initial test tube type shape parison is obviously deformed into a vastly different shape. And we can start pushing that deformation even further. So here we've got a bird strike simulation where the bird is hitting this particular plate and is obviously collapsing. And on the right again, fans on a blade hitting an object and actually going through and breaking and fracturing, and then what happens to those fragments as they go through. Obviously, as we're getting into these more and more advanced setups, you're going to need more and more advanced information in the material, hence why I mentioned about the material library and those options that are in there. But going even further, you can have, so here we've got a situation where we've got a fluid inside a structure, and we actually need to have that fluid inside the structure to get the correct response of the structure under these deformations. An empty bottle will collapse very differently to a full bottle because you've got to also deform that fluid that is going through. Pardon me. I'm going to stop. Okay. So those are just basically ideas. If you've not seen these types of analyses, these are things that can be done. Just really want to put it out there that if you have a situation and it seems like you probably can't analyze it, talk to your reseller. It may well be possible to do that. You just might need to use a different tool. And obviously here we're only really talking structures because that's kind of our expertise. But then there are things like EMAG and CFD and things like that as well. The last bit I want to mention quickly is about fatigue. So I bring this up because not everybody, is everybody aware that you can actually analyze and simulate for fatigue? Not just stress like in FEA, but actually for fatigue. Is that something that you're aware of? Yep, there is a durability module inside SOLIDWORKS, so I was hopeful that you are aware of this. The question usually is going to be more a case of why do I need to analyze for fatigue? And for a lot of cases, to be honest, you don't. A stress-based analysis and reducing the stress below a limit will often be enough to make sure you don't have fatigue problems. But then you get into situations like this. We've got a steering arm, and under a low initial load in red, and then a repeated blue in low load again, this fails at the peak stress location, which is around the mounting bolts. If we do a high initial load and then keep repeating that high initial load, it fails around the peak stress location at the mounting bolts. The question then becomes, what happens if you have a high initial load followed by low-level loads repeated? Would anybody like to make a guess? Okay, hands up if you think it would fail at the mounting bolts, because that's the peak stress location. Only me, a couple of you? Okay. Yeah, most of you presumably maybe have either seen this before or realized that I would not be putting it up here if it was as straightforward as that. But with the information I've presented, that is really the only conclusion you can come to. Pardon me. However, they knew that this was not the case. They were testing these steering knuckles and they break in the arm. That is really tricky to explain just using finite element analysis. So that is why a durability analysis is very useful, because you're dealing with the fatigue damage, and we did indeed predict the failure will be at the arm in this particular load case, which is why they were talking at a customer conference and why those of you who kept your hands down were actually correct. So the last bit I want to talk about is welded fatigue. See what time we got? Yep. So for fatigue, as we can see, having a stress concentration will tend to drop the life that you get. When you have a welded structure, it is great for joining things together. It is horrible for fatigue. Now, I won't get into details here. What I really just want to bring about is you can see that this is significantly lower life and a different curvature to parent plate material fatigue. That generally means you're going to need a different approach in order to get an accurate result for a welded fatigue problem. And as you can probably imagine by the fact that I'm mentioning it here, we do have the ability to do welded fatigue. There's a couple of different things. If any of you are interested in more details on that, feel free to reach out to me. I just at this point want to let you know that there is that ability. We can not only analyze parent material, we can analyze welds as well, and the life is not the same between these two approaches. So, to summarize, because we've gone through a lot of topics here, as I mentioned, you may well want to think about things on the cloud, particularly as you start getting bigger and more complex models, and they've got more interactions and more involvement, and they just need computing horsepower. We can do analysis of what seem like fairly complex things. Well, they are complex things, let's not. But we can do analysis of them. The main one that I would like you to think about and take away is this idea of general contact. It is different, and it's something that, like I said, in 3D experience, we have both contact pairs and general contact. I'll be honest with you, since we've had general contact, I've never used contact pairs because it's still far easier to set up here, so why bother with that extra step? I mentioned this, we've got the model scenario results. This can be more complicated than everything all in one study. There is no difference here. It is 3 different sections. It does give you more flexibility. It does give you more ability to look into things, and that's how we sort of end up with things like this and this. But the number one recommendation, if you only remember one thing from here, and you're going into 3D experience, it is a very different interface to SOLIDWORKS Simulation. But the assistant keeps everything all together in one place and even gives you a kind of little traffic light guidance as to what you need to do to get through that. So you can set up most things here and then start delving into the more fidelity of the model scenario results. So that's everything we had. We'll open it up for questions, although I don't know if somebody else is in this room afterwards, but if they are, we might need to do that out in the hall.
Nobody fell asleep. I'm happy.